All right. So we'll get started then. Okay. Can you all see that? Cycloalkanes, chair conformation, curved arrow formalism?
Yeah.
Okay. So that's what we're going to be talking about today. And so let's just go a bit through our learning objectives. So we're first going to introduce what cycloalkanes are. We're going to talk about the ring strain that is associated with cycloalkanes. And then we'll talk about a couple different main cycloalkanes that you'll encounter in 3570. And after that, we're going to move into the curved arrow formalism that is going to eventually become your best friend throughout your organic chemistry journey. So the first question we're going to ask is, what are cycloalkanes? So cycloalkanes, you've seen a couple of them before, but all they are a cyclic saturated hydrocarbon molecule. And all I mean by that is you have kind of this closed ring of carbons attached to each other. For the time being, don't worry about knowing these names. You will eventually need to know all of these names, but it pretty much just follows what you've been learning so far, right? With the prop meaning 3, but meaning 4, pent is 5, hex is 6, hept is 7. So that means you're going to have closed chains of carbons connected to each other. And based on the number of carbons you have, you're going to have a very specific name for the compound. And so it's also important to note that later on in 3570, although we're only going to be covering single ring cycloalkanes in this lecture, you will be met by polycyclic alkanes. And all I mean by that is just molecules that have, sorry, what? Molecules that have 2 or more cycloalkanes that are joined to form multiple rings. So when I say that, you could have something like this, where all you have are 2 cyclohexanes that are joined together. So now let's go on to a little bit about ring strain. So cycloalkanes, they're a cyclic arrangement of carbons. And one of the things that we have to think about when we're talking about these cycloalkanes is ring strain. So ring strain, all it is a destabilizing effect that is really an important feature in determining which cycloalkanes are going to be the most stable, right? Because in chemistry, and specifically organic chemistry, what we need to think about is how can we make this structure more stable? So the ring strain that we're going to focus on, there's 3 parts to it. There is something called steric ring strain. There's going to be torsional ring strain. And lastly, you're going to have angle strain. And let's just kind of walk through these main ones really quickly. So first, starting off with steric ring strain, all we mean by that is the crowding of groups in a ring. So if you have a ring and you have things coming off of that ring, right? Here you have kind of your chain and you have things that are coming off of that ring. You can think of it as if you have enough things coming off of that ring, they're going to be bumping into each other, right? when you were thinking about Newman projections, you had to look at the Newman projection and think about what conformation is going to make this Newman projection more stable, which one is going to be more unstable because of the sterics. So that is the first part. We have sterics, and when we have things coming off of rings, we can have steric strain on the ring. So that's the first factor that's going to influence which rings are going to be more stable. The second factor is called torsional strain. So torsional strain, all it is an intramolecular strain that happens because of bonding interactions between eclipsed groups. So in that, the word eclipsed group should already ring a bell, right? It's something that you talked about on Wednesday when you were drawing your Newman projections. So it's really similar to torsional strain or to steric strain. So when we're thinking about torsional strain, all we're thinking about is, are these groups, are they overlapping each other? Are they in front of each other, right? So when you drew your Newman projections, you were thinking about, okay, if we have a Newman projection that looks like this, right? This is going to be your eclipsed conformation. That means that you're gonna have these groups right in front of each other when you do your Newman projection. And if you have them in front of each other, that's going to make your molecule more unstable, right? In chemistry, things want to spread out and be as far apart from each other as possible. So when you start adding torsional strain, when you start making things block each other or make things cover each other up, you are adding an increased amount of energy to your molecule. So then the last piece of ring strain that we're going to think about is angle strain. And so angle strain is present when there's pore overlap between atoms, right? So if we think back to carbon, it usually likes to make these sp3 bonds. So let's draw in our sp3 bonds, right? We have these sp3 hybridized orbitals. And remember, when we're thinking about sp3, right, the angle that we want to have between that is 109.5. But when you add in angle strain, you start going away from whatever that ideal bond angle is supposed to be. So this might not be completely clear yet, but when we move on to our next example, it'll be a little bit more clear. And so let's just go back up here really quickly and think back to these basic cycloalkanes that we've proposed. So we have cyclopropane, right? And if we think back to our geometry days, these internal angles right here should be 60 degrees, right? If we think back to cyclobutane, right, 4 carbons in a chain, these internal angles should be 90 degrees. If we think about cyclopentane, these internal angles should be 108 degrees. If we think about cyclohexane, these internal angles should be 120 degrees. So based on that and what we just learned about angle strain and how all of these carbons right here, right, they're all sp3 hybridized carbons, right? All of these carbons are sp3 hybridized carbons, right? They all have 4 things coming right off of them. But from what we've just seen on these angles, all of these angles, none of them are exactly 109.5 degrees. And that is going to be kind of one of the big driving factors in determining what's going to be the most stable. So there was a scientist, his name is Adolf von Baeyer, and based on what we just talked about and about these specific kind of angles that you would see if this molecule was planar, right? If all of the carbons were in the same plane, which we know is not true, right? Because carbons like to form the tetrahedral arrangement. Von Baeyer predicted that cyclopentane, this one right here, should be the more stable cycloalkane because the bond angles are the closest to 109.5, right? And bond angles of sp3 carbons are 109.5. And cyclohexane, he thought, should be the least stable, but he was wrong. And the reasons why he was wrong has to do with the fact that these cycloalkanes, they can actually adopt a three-dimensional, a 3D arrangement. They can warp the way that the carbons are connected to each other in a way that makes some of these cycloalkanes more stable than you would think, right? Von Baeyer thought cyclohexane would be the least stable, but it turns out that cyclohexane is going to be the most stable. And that's because it's able to go away from this 2D arrangement, right? In the 2D arrangement, we know that the bond angles should all be 120 degrees. If it's actually able to go away from that 2D arrangement and kind of twist in a way that makes it more stable, it ends up becoming the most stable cycloalkane. So now let's kind of revisit the ring strains. So we've talked about steric, torsional, and angle. And we also need to note that when we talk about steric strain and how it's different from torsional strain, steric strain is something that's going to apply only when you get to the larger cycloalkanes, things that have 6 or more carbons. Ring strain or torsional strain is going to apply to all of the cycloalkanes. So I hope that part has made sense so far. So now let's look at the first cycloalkane. So the first one is going to be cyclopropane. That's the simplest cycloalkane you can have. It's the simplest, smallest number of carbons that you can put together to make a ring, all right? So now if we look at this, let's think about the three different ring strains that we've talked about. So the first one was steric, but in this case, we wouldn't even think about steric strain in cyclopropane, right? Because we said steric strain is not something we consider until we get to cycloalkanes that have 6 or more carbons in them. So this doesn't really matter for the time being. So the next one is torsional strain. And that's when you have all of these eclipsed groups going on, right? So if we look at this 3D kind of structure, and this one too, if you can imagine it, right, and you look down any of these bonds, you look down this way or you look down this way, what you'll see is that all of these hydrogens right here, they're going to be overlapping each other. And I hope that's kind of clear in that structure. So you'll have all of these hydrogens, including the bottom ones, they're going to be kind of in front of each other. And from what we learned in Newman projections, when you're putting things in front of each other, that's going to raise the energy. So right off the bat, we know that a torsional strain in cyclopropane is going to be high. Now, the last thing we need to think about is the angle strain, right? So if we look at this kind of depiction of cyclopropane, what we can see is that we're not getting very good overlap of these orbitals, right? Because carbon likes to form these 109.5 degree bonds between things. So ideally, this carbon, it would much rather have its bond, its sp3 orbitals kind of facing out like this. But because of the fact that it's kind of confined to this triangle, these orbitals aren't able to really overlap. So you only get this little amount of overlap right there. And you also only get this small amount of overlap there and this small amount of overlap there. So from that, we can see that the angle strain in cyclopropane is also going to be very high. And so that begs the question of why should we care about this ring strain? Why are these steric, torsional, and angle strain factors, why are they important? And that's because cycloalkanes, they tend to give off a very high non-favorable energy. And we don't want ring strain because the increased energy causes heat to be released, and the energy ends up being stored in the bonds plus the molecules. And it leads to a ring that is unstable and very reactive, right? And things, if something is very reactive in chemistry, it tends to be more unstable. So the ring strain ends up affecting the structures and the functions of these cycloalkanes, and it kind of tells us which cycloalkanes are going to be more stable. And one thing that I didn't mention yet is what is another way that we can kind of determine the presence of ring strain, right? We talked about these more quantitative metrics, right? We can look at the steric, the torsional, and the angle strains, but another way you can do that is through something called strain energy. And all that is it's based on the heat of formation of the cycloalkane minus the heat of formation of the N-alkane, right? And so N-alkane, we've kind of covered them already in the first two lectures, but all that means is it's just a normal alkane. It's a chain of carbons. So from this, you can kind of get an intuitive idea of these cycloalkanes and of the strain energy, right? If you need to put in a lot more heat to create the cycloalkane compared to the normal alkane, the strain energy is going to be positive, right? And so that makes it more unfavorable to make this cycloalkane, where you could just, instead of, where you could just have it in the linear shape. So let me just give you a few. What? So let me just give you a few important values, right? So let's look at cyclopropane. Let's look at cyclobutane. Let's look at cyclopentane, and then cyclohexane. And this is going to kind of help re-solidify what we said in the beginning, that cyclohexanes are actually going to be the most stable. So if we write down what these ring strains are, the ring strain for cyclopropane is 113 kilojoules per mole. The ring strain for cyclobutane is 109 kilojoules per mole. The ring strain for cyclopentane is 25 kilojoules per mole. And the ring strain for cyclohexane is going to be 0 kilojoules per mole. So from that, you can tell that cyclohexane is going to be the most stable out of these, followed by cyclopentane, then cyclobutane, then cyclopropane. And so from that, right, and all that we just know, propanes are going to be the most unstable cycloalkane. And in fact, they're actually going to be stuck in this planar arrangement. And there's not going to be any internal rotation between these bonds because of how small the molecule is. So when I say internal rotation, I just mean there's not going to be any rotation around these carbon-carbon bonds right here. Right, so just to recap the kind of important attributes about cyclopropane, it's stuck as a planar molecule. It has poor orbital overlap. And because of these poor orbital overlaps, it has weaker bonds. And lastly, it's not going to do what we call puckering, which all that means is that it's going to kind of flip in on itself. It's kind of hard to explain with cyclopropane, but we'll see more examples where the molecule actually does pucker. So it's going to have high eclipsing interactions, right? So that means high torsional strain. So if you see eclipsing, you can think of it as torsional strain. So that was the first one. And we're gonna skip this example problem for now. And we're gonna look at the next cycloalkane, and that's going to be cyclobutane. And right off the bat, what you can see is that you're actually going to get this weird puckering that's going on right here, right? If we think back to what von Baer thought, he thought that the molecule would just be a two-dimensional kind of just flat square. But what we actually end up seeing is that it'll pucker where this carbon, you can think of it as that carbon, is going to fold up. And when it folds up, all it's doing that for is to make the molecule more stable. And this conformation that we have here, it's called the butterfly. So like I said, all the molecules, they want to try to kind of twist their angles in some way to make the molecule more stable. So let's kind of talk about the important aspects of cyclobutane. So the first thing is angle strain. Does it have angle strain? And what we'll come to realize is that it does. And what is also an interesting thing is that normally these bond angles, they should be 90 degrees. But by puckering, the cyclobutane, it'll make this new bond angle right here, this one, these ones, it'll make it an 88 degrees, right? Which is even further away from that ideal 109.5. So it kind of begs the question of why would it do this? Why would it increase the ring strain by increasing angle strain? And so it's doing this just to have a trade-off, right? You're decreasing this angle, but what you're ending up doing is you're changing the eclipsing interactions, right? So it's might not be clear to see yet, but from puckering and from raising this carbon up like that from kind of this flat plane, what it's doing is that it's only allowing these hydrogens to eclipse each other. You have eclipsing hydrogens right here at the bottom on opposite carbons, and you have eclipsing hydrogens at the top on opposite carbons. And that's vastly different from what it would have been, where if it was completely flat, you would have had hydrogens, all four of them at the top would have been eclipsing each other, and you would have had kind of this, where the two on the side, those would have eclipsed each other, and the two on the other side would have also eclipsed each other. So by doing what we call puckering, it turns into the butterfly, and it increases the angle strain. But by increasing the angle strain, it's going to be decreasing the torsional strain. And from the heaps of formation that we saw previously, where we saw that cyclobutane is at 109 kilojoules per mole, we know that it's going to be more stable than cyclopropane. So this increase of angle strain to have a decrease of torsional strain does make it a more stable molecule. And because of that, cyclobutanes are a little more stable than cyclopropanes, and they're a little more common in nature. So now the next molecule that we're going to talk about is cyclopentane. And these are going to be the second most common cycloalkane found in nature. And so once again, let's just kind of look at the different types of strain and how they affect the molecule. So first off, with angle strain, right, in the two-dimensional drawing of a cyclopentane or a pentagon, you know that these bond angles are going to be 108 degrees, which is the closest to the bond angles of an sp3 hybridized carbon. So from that, if that was the only kind of strain that we had to take into account, you would think that cyclopentane is the most stable, just like von Baer thought. However, we also have to think about the torsional strain. And so what cyclopentane actually does is, if it was all planar, you would have all of these hydrogens at the top right here, you would have all of them eclipsing each other. But by puckering, there's that word again, right? Where you're kind of increasing or changing the angles, you're kind of warping the structure by puckering, the cyclopentane is able to decrease the torsional strain, right? So it's going to decrease the torsional strain, and it'll make kind of this structure that we call the envelope conformation of cyclopropane, I think, yeah, that we call the envelope that we call for cyclopentane. What you end up seeing is that only these back hydrogens are going to be eclipsing each other, right? And you'll have very little eclipsing interaction there, but that's a small amount compared to what it would have been if all of the hydrogens had been in the same plane by not having this puckering. So that was kind of the torsional and the angle strain aspect of this. And so we lift up this little carbon head, let's call it, we lift it up and it decreases our torsional strain. We have a lot less eclipsing interactions going on. So that makes cyclopentane the second most common cycloalkane. And like we said before, you're not going to have steric strain in here either, because we don't get steric strain until we get to the carbons, or we get to the cycloalkanes with 6 or more carbons. So now we're going to look at our last kind of cycloalkane, and this is going to be the most important. And that is going to be cyclohexane. So what cyclohexane does, right? Once again, if it was just in this planar arrangement where all the carbons were connected to each other in kind of on the same plane, you would have so much torsional strain. All of these hydrogens would be eclipsing each other on the top, right? That's what the wedges mean. All of these hydrogens on the bottom would eclipse each other. So what cyclohexane does is it's going to adopt something that we call the chair conformation. Now, this might be a little hard to see, but you can think of it like this, right? And instead of being kind of like that, right? So that's what the two-dimensional depiction of cyclohexane would look like. What cyclohexane does, it does the puckering, right? And unlike the cyclopentane where it puckers to make an envelope, cyclohexane is going to pucker to make what we call the chair. And if you kind of just look at this, you can see how this is happening, right? You're bringing this bottom carbon, you're kind of folding it down and bringing this top carbon, you're kind of folding it up, and it leads into this. And so it might be a little hard to see, but it looks almost exactly like a chair if you think about it, right? You have right up here, let's picture that as our headrest, and let's picture this bottom as our footrest. And so let's go around and label all of our carbons. We have 1 carbon, 2, 3, 4, 5, 6. And so the reason why this ends up the reason why this chair conformation makes cyclohexane the most stable cycloalkane is because it completely eliminates any of the torsional strain. So if we think back to our different types of strain, we have torsional, we have angle, and this time our steric strain is going to be a factor, right? Because it starts being a factor when you have molecules with 6 or more carbons. So our steric is going to be something we're going to look at, but let's first just think about torsional. So let's think, right? We have kind of this chair right here. This is a better picture of it. Let's use that one. So we have that chair, right? You have your headrest right there and your footrest up here. Now, these carbons, all of these that are kind of in on the ends, right? There's all of our 6 carbons. All of those carbons, those are going to be sp3 hybridized. So that means that we're going to need to have things coming off of those carbons. And so if I drew, so we're going to have things coming off of those carbons. And if you look at it, right, those things that are coming off of the carbon, we have this and this, this and this. They're not going to be overlapping at all. I hope that's kind of clear how they're not going to be overlapping. But imagine you just drew a Newman projection for it, right? You would have kind of this, this thing coming off of that carbon. You would have it in between the back of the other carbon, of the back carbon. This one, it's not going to be overlapping anything. So I hope that's kind of clear how we don't have any eclipsing interactions when we switch into the chair conformation, when we pucker the cyclohexane into the chair. So now let's look at angle strain. And because of this puckering, right, normal cyclohexane should be 120 degrees, but the puckering allows all of these carbons right here to actually end up being 109.5 degrees exactly. So that's going to completely decrease our angle strain down to 0. So now we have no angle strain and no torsional strain. And then we're going to later talk a little bit about the steric strain. So cyclohexane, it's going to have steric strain, but for now, let's just ignore that. Let me bring your attention to just one last aspect of cyclohexanes that are going to be important. And you might have been reading this on the slide, but that is going to be the equatorial and the axial positions. So axial positions, all we mean by that are just the things that are coming off of these carbons that are going up and down. Right? They're going up like the axes of the chair, right? Because things that are on these carbons, it's sp3 hybridized, so there's always things that are going to be kind of going out, right? You can think of this as the legs of the chair, or as the legs of a tripod, and then this would be the top of that tripod. So these are the axial positions, things that are coming off of that carbon in that they're going to be sticking up in the axes. Now there's also the equatorial positions, right? Because if we look back at these carbons, there's going to be things coming off of those carbons. And if we have one thing in the axial position, this carbon only has 3 things attached to it so far. So it needs to have one more thing attached to it to make it sp3. And so that thing is going to be in the equatorial position. And all that means is that it's going to be in the same plane as the rest of the chair. It's going to be kind of parallel to the rest of the chair, if you think of the chair like that. So we'll have the axial and we'll have the equatorial positions on cyclohexanes. And it's important to know these because those are going to play a role in the sterics of the chair. So I hope that was kind of clear. We're going to later get into drawing the chairs, but a little bit of time is passing. You want to just
Hey, Corel,
yeah.
Your audio is like very choppy.
Is it?
Yeah, it was right now. I couldn't understand what you were saying.
How's that? Is that better?
Yeah.
Okay. So Brandon, did you want to just start your part of the lecture and then I can either record the rest of cyclohexanes, or do you want me to just finish up with cyclohexanes?
About how many more minutes do you think?
Probably like 10-ish more minutes.
Okay, I think that's fine. I can go through my stuff fairly quickly, so you can just finish up.
Okay. So we kind of talked about these axial and equatorial positions. And so let's just do this example problem really quickly. And you guys can just shout out whether these positions are going to be axial or equatorial. So let's just start off with one. Every carbon is going to have one axial and one equatorial. So is this going to be axial or equatorial?
Axial.
Yeah. What about this one?
Equatorial.
Yeah. And then you can just shout them out as I go. This one?
Equatorial.
Equatorial.
Yeah. This one?
Axial.
Yeah. So I think you guys kind of get the gist of that. So there's one last thing that is kind of important to mention on these, and that's that axial and equatorial all it means is it just tells us whether it's going to be kind of axial, it's going to be the axes for the chair, or it's going to be kind of parallel to the equatorial position on the chair, right? But there's also one last part to that, and that's whether it's up or down. So if you guys kind of look at what we were just thinking about, right? This is axial, right? But this is also axial. And the difference between these is that this is axial going up, and this is axial going down. I hope that part is clear. So you can have axial going up and axial going down, and they're going to alternate around the carbon. If this is going to be an axial going up, the next axial you see as you go clockwise is going to be an axial going down, right? When you go to this carbon, this is going to be an axial going up. Then the next axial is going to be an axial facing down. So I hope that part is clear. But however, you can also have equatorial going down and equatorial going up. And it's the same kind of concept, right? We can agree that this is going to be an equatorial, right? We can also agree that this right here is going to be an equatorial. Can you guys see that?
Yes.
Okay. But the difference between this equatorial and this equatorial is that one is facing up, right? But the other one is facing down. So we're going to have axial up, axial down. We also have equatorial up and equatorial down. And like the axials, they're going to alternate on the carbons. So if this one right here is an equatorial going up, this equatorial is going to be down. On here, this carbon, this equatorial is going to have to be going up, right? And if we look, this is the equatorial, and there it is going up. And we don't have too much time to get into kind of drawing the chairs. I can stay after the lecture just to show anyone who's interested, but we will be posting the notes that'll have more detail on how to draw the chairs. So then the last thing, we also have videos on this that kind of explain the chair and kind of show you how the chair works. There's kind of two more important parts of the chair that are important. And the reason why we care so much about these cyclohexanes and we're going so much more in depth into cyclohexanes is because of that 0 kcals per mole or kilojoules per mole heat of form strain energy, right? So it's the most stable, so it's the one that we're going to care about the most. So one of the two more things that we consider when we do a chair flip, when we do the chair conformation, is something called the chair flip. And all that is that this chair right here, similar to how in your Newman projections you were able to do kind of rotations around bonds, this chair is going to be able to do what we call a chair flip and turn into this chair. And it might not be easy to see yet, but let's just kind of draw out the structure of our chair. You have your headrest and your footrest here. And right here on this chair, we have our headrest and we have our footrest. And if you look at it, right, all that's happening is that this footrest that's here, all it's doing is it's flipping up. And this headrest that's right here, all it's doing is it's flipping down to make this chair. And that is just the chair flip. That is, that's going to be important for the last bit of strain that we talked about. It's going to be important for the steric strain. So our chairs, they're able to flip and kind of change from one chair flip to the next, to the other. And that is going to be important in sterics because what it's going to do is it's going to put things that are axial, it's going to put them in the equatorial position. I hope that's clear that we just went from axial, right? It was the methyl group was axial. but now it's going to be equatorial. And it's also important to note that even though it's going from axial to equatorial, it's still facing up, right? It's going up, and this axial is going up. So all the chair flip does is it's going to move things from equatorial to axial or vice versa, but it's going to conserve the direction that the things are pointing in. So if something was facing up axial, it's going to be, after a chair flip, it's going to be up equatorial. If something was down axial, you do a chair flip, it's going to be down equatorial. And we have a video in the lecture slides that will be posted that will explain a lot more on that. And so, as I mentioned before, this chair flip is going to be important in sterics because of this last concept called 1,3 diaxial interactions. And all that means is that you're going to have steric interactions because of the ability for these kind of larger groups that are in the axial position. They're going to be interacting with each other. You can think of it as their electron clouds are going to be repelling each other. So that is the 1,3 diaxial interactions. And specifically, let's just look at this carbon right here, the headrest carbon. It has this axial methyl group, right? And let's call that carbon 1. If we go around 2, we make this carbon 2. We go around, we make this carbon 3, right? We're going to get a steric interaction between the things that are axial coming off of carbon 1 and carbon 3, right? And that's if we go around that way. Let's go around the other way. Let's go around counterclockwise. Let's make this carbon, carbon 2. Let's make this carbon, carbon 3. You're going to get another steric interaction with this hydrogen. So I hope that's kind of clear with just the 3D kind of depiction on that. So let's look at this in kind of a Newman configuration or Newman projection, right? If you drew out the Newman projection for this chair looking down this bond like that, you're going to end up with this Newman projection. And to just make the point of 1,3 diaxial interactions a bit more clear, what that's going to do is you're just going to have this CH3 group and this H, right? You're having them right next to each other. Specifically, they're gauche to each other. So now you're putting this bulky CH3 right next to hydrogen, and that's going to be sterically unfavorable. So a couple of practice problems, but we will skip those, and we'll just look a little bit about this mechanism for the chair flip. So the video that's going to be posted, it'll show it in, there will be a person doing the actual chair flip with the model kit, but all you really need to know about this chair flip is how we are going from what's known as the chair, right? These are the chairs, and as you go up and down this energy diagram, you're getting kind of these intermediates of the chair flip, right? We talked about how the chair flip is, all it is that the headrest and the footrest carbons, they're going in opposite directions, right? Well, things happen in between that change. And all of this is just kind of describing the things that are happening in between that change. And in the lecture notes, I'll post a little bit more about what's leading to kind of these changes in energy as we go, as we do the chair flip, but that is it. So I will turn it over to Brandon.
Hey everyone. So for those of you who don't know me, my name is Brendan. I'm your other Friday lecturer. So just a couple quick things before I get started. One suggestion, I would highly suggest reading the textbook. In my opinion, unlike the Gen Chem textbook, I found that to be really unhelpful. But both the content in the Orgo textbook and the practice problems I find to be very helpful. And I definitely used that when I was studying for exams and whatnot. The second thing is the topics that I'm covering today in this lecture are going to be relatively base level. So again, I would suggest going back to the textbook for more information. So let me try to share my screen. All right, can everyone see this okay? Okay. So the first thing I'm going to be talking about is the curved arrow formalism. So you have already seen this. Oops, let's make sure this is this still recording or is it not recording?
Yeah, it's still recording.
Okay, good. So you've already seen this on the first two lectures and even in the first study group worksheet, but we're gonna just cover this now in a couple different scenarios. And yeah, so we'll see. So the general principle for the curved arrow formalism is that the arrow points from the electron source to the electron acceptor. And so here's a very basic, just pictorial representation of that. So we have the electron source, and then the arrowhead goes to the electron acceptor. So let's get into some examples as to where this shows up. So the first, like you've already seen, is in resonance. So the arrow for this first resonance structure, right, we have the free electrons on the nitrogen come down and send up the electrons in the double bond onto the oxygen, giving you a positive formal charge on the nitrogen and a -1 formal charge on the oxygen. Okay, so I'm not going to really cover the resonance because we've already covered that, so I just want to introduce you to the different scenarios in which the arrow formalism is used. Okay, so for this next example, very similar situation. We have the free electrons on the nitrogen along with the plus charge on the carbon. So we have the arrow pointing from the electrons on the nitrogen into the location where the electrons are going to end up. And that gives us a new picture, which looks something like this, with our positive charge now on the nitrogen. Okay. Now, for the last one, these pi electrons in this benzene molecule can also rotate around the molecule. Okay, so to show that, we have arrow coming in like this, which sends the next set of electrons into the next carbon-carbon single bond, and finally like this. And so we get a final representation that looks like this, with the double bonds now in different locations. Okay, and so that's shown here. Now this one. So we've already seen instances of carbocation showing up in both previous lectures and in study group worksheets. So this situation right here, where the X represents a halide, whether that be chlorine, bromine, iodine, gets basically ejected from the molecule. And so you'll see this in a couple of weeks when we start talking about different reactions, such as the SN1 and E1 reactions where the carbocation is formed in the process. So we have the electrons in this bond actually get moved onto the halide, and that separates them into two different ions. Okay, so we get the carbocation formation, which is basically just a positive charged carbon. So it does not have a filled octet, leaving it with a positive charge. Okay, and then we have our anion produced by the electrons being moved onto the halide. Okay, so again, this stuff is going to be covered more in depth in a few weeks. I just wanted to show you different instances in which the curved arrow formalism is used. So the next topic, we have Bronsted acids and bases. This is what you're most familiar with from 2080 and 2070, where your Bronsted acid is the H plus donor and the Bronsted base is the H plus acceptor. In the formalism, right, we have water, in this case, acting as the base. The electrons come over and they attack the hydrogen, which sends those electrons back onto the rest of the base, or the acid, I mean, forming the conjugate base and conjugate acid, which in this case is just the A minus and the H3O plus. So any questions on this? Let me know if I'm going too quickly. I think I tend to speak kind of fast. Okay. Now this is probably a new topic, which is Lewis acids and Lewis bases. Okay. So just to give you a definition, the Lewis acid accepts an electron pair to form a new covalent bond, and the Lewis base donates an electron pair to form a new covalent bond. So if you look at this case of the reaction between BF3 and ammonia, we have the free electrons on the nitrogen, which in this case is our Lewis base, since it's donating the electron pair, attacks the free pi orbital, or p orbital, I should say, on the BF3. Okay, so these electrons actually get displaced into this orbital, and the result of that displacement is the formation of a new covalent bond between the boron and the nitrogen. Okay, so notice that in the process of the reaction, the overall charge is conserved. So that's going to be an important theme. It may look awkward in some situations. With certain molecules that you wouldn't expect to have positive charges end up having positive charges in order to maintain the overall charge of the reactants and products. Is there any questions with this? Okay. So if we look at another example, we have the fluorine, in this case, acting as our Lewis base. And again, BF3 acting as our Lewis acid, which is accepting the electrons. And so the electrons from the fluorine are donated into the free p orbital of the boron. And again, you get the formation of the new covalent bond with overall charge conserved. Okay, so I have some practice problems, but for the sake of time, we will continue on past these, and these problems will be available for you to try. Okay, now this is a very important concept in organic chemistry, and that is of nucleophiles and electrophiles. So to, again, give you the base definitions that the textbook gives you, the nucleophile is means nucleus loving and is a species that donates an electron pair to form a new bond. The nucleophilic center is the actual atom that is doing the donating of the electrons. Then the opposite, we have the electrophile, which is electron loving, which is the species that accepts the electron pair to form the new bond. And the electrophilic center is the actual atom that is doing the accepting. And then lastly, we have our leaving group, which is the atom or group that is expelled when the electrons are accepted from the nucleophile. So a bond is broken in the process, okay? And so we'll go through this top reaction in a little bit, but I wanted to give you a little bit more practical information other than these definitions that will help you to identify the nucleophile versus the electrophile. Okay, so a nucleophile is, it has a region of high electron density. Oops. Electron density, and so by that you'll see that the nucleophile will either have a full positive charge or a negative charge or a partial negative charge, okay? Now, the electrophile, on the other hand, has a region of low electron density, which you will see usually in the form of a plus charge or a partial positive charge. So the partial charges are very important because in many molecules, you aren't going to have that full charge. But because there are differences in electronegativity, electrons will tend to localize around a particular atom, drawing away electron density from the other atom that it's bonded with, leaving with a partial negative charge and a partial positive charge, okay? So let's look at some examples of nucleophiles, okay? And so one of them, we have this ion, okay? So this is the epoxide ion, anion. And so this anion has free electrons around the oxygen, which it can donate to form new bonds, okay? Now, a slightly different example is we have the, ethoxide. Now we have the acid version of it, okay? Not the base, but it still has free electrons, okay? And so notice that the oxygen is more electronegative than the carbon. And so we end up with a partial negative charge and a partial positive charge on this, still making the oxygen available to act as a nucleophile. Another example, which might seem somewhat strange at first, is this cycloalkene. So we haven't talked about alkenes yet in depth, but again, it's just a carbon chain, or cyclic form, which contains a double bond. So pi bonds are areas which contain high electron density. So in reactions, these pi electrons are actually able to act as a nucleophile and donate to the electrophile to form a new bond in a reaction, okay? So again, a number of these things might look kind of strange at first, but it just takes practice. So look for areas for nucleophiles that have high electron density. In a few lectures, they'll be talking about what makes a good nucleophile and how those play important roles in reactions. Okay, so now let's take a look at electrophiles. One example here is this with the carbonyl group. So again, we have the oxygen pulling electron density away from the carbon atom, that it's bonded to, leaving with a positive charge, a partial positive charge, excuse me, on that atom. And so this partial positive charge actually allows the molecule to act as an electrophile. So other nucleophiles can take advantage of that sort of lower electron density and use it to form a new bond at that particular carbon. Now, the next example kind of ties in a previous topic that has been discussed, which is resonance, and how resonance can play an important role in determining electrophilic sites or nucleophilic sites. Okay, so we're going to look at this molecule, which has an alkene and an aldehyde group. If you remember from the functional group list that you've already seen before. Okay, so one possible resonance structure for this is if the electrons move up onto the oxygen, which would give us a minus charge here and a plus charge here, because we have left the carbon without a filled octet, and so it gets that positive charge there. So this carbon atom is able to act as an electrophile and an electrophilic center. Okay, so alternatively, another possible resonance structure for this is if this double bond moves here and then also sends up the electrons again. In this case, you get something that looks like this. Now notice the positive charge is in a different location than the previous resonance structure. So due to resonance, this particular molecule right here actually has the capability of having two electrophilic sites and electrophilic centers. So that's important when we talk about reactions and carbocations, which we'll get to next week. So if we come back and we take a look at this reaction from the slide of definitions, we can identify this particular molecule, the ammonia, as a nucleophile. Okay, so the whole molecule is the nucleophile, but the nitrogen is the particular atom that is doing the actual donating of the electrons, and so that is what we call the nucleophilic center. So with that, can anyone tell me what you think the electrophile is and what the electrophilic center would be?
The carbon?
Good, yeah. So the carbon is going to be the electrophilic center, and the whole molecule is considered the electrophile. Okay, does that make sense? That differentiation between the particular atom that is actually receiving the electrons and the actual the whole molecule, which encapsulates all the atoms. Good. So we have the electrophile and the electrophilic center. Now the last thing that was mentioned on the definition page was the leaving group, which is results from the breaking of a bond and the electrons actually moving on to this group kind of ejecting it from the original electrophile. So can anyone tell me what the leaving group in this case would be?
The BR.
Awesome. Yes. Oops. So the bromine is the leaving group in this case because it's receiving the electrons from the bond that is breaking when the nucleophile attacks the electrophile. Okay, so if you'll notice, the product of this reaction is a new covalent bond formation with the resulting leaving group, which in this case is the bromine anion. Okay, so yep, here's our leaving group. And so now I have some practice problems. So in terms of content, that is all I have for you. So again, like Corel is willing to stay longer to work through some of these problems if you'd like. But know that the problems will be posted along with the answers. So that's all I got. Okay, so if you want, I can give you some time to work through these problems. So in the first set, it's basically just practicing identifying the nucleophilic center, electrophilic center, and the leaving group. Okay, so why don't you take a minute or two to try these problems, get an idea, and then we can talk about them. All right, how about we take a look at the letter A, which you might have noticed is the reverse reaction of the one that we just went through. So can anyone tell me what the nucleophile in this case is, or the nucleophilic center is? So which atom is going to be donating the electrons?
Bromine.
Sorry, say that again.
Bromine.
Good, yep. So the bromine in this case is our nucleophilic center. And what is our electrophilic center? which atom is receiving the electrons? Or which atom is receiving the electrons?
The nitrogen.
Close. So take a look at the products and basically identify which where the new covalent bond was formed. So did the bromine form a new covalent bond with the nitrogen or the carbon?
The carbon.
The carbon. Good. So knowing that, which one is the electrophilic center?
The carbon.
Good. Yeah. So the carbon is going to be our electrophilic center. Okay. And that leaves one thing, which is the leaving group. So which piece of our, in this case, electrophile is the leaving group?
Nitrogen.
Awesome. Yes. So in this case, the leaving group encapsulates like everything that's attached, everything that leaves. Okay. So in this case, the leaving group is going to be the nitrogen and everything attached to it. Okay. So the nucleophile comes in, right? And it attacks this carbon at the electrophilic center. Then this bond, right, connecting the carbon and the nitrogen breaks. And so these electrons are sent off to the nitrogen. And that you can see in the products, right, where we have this new covalent bond formation along with our leaving group, which is just the portion of the molecule that left, that was basically ejected when the nucleophile reacted with the electrophile. Make sense? So how about for B, which atom do we think is the nucleophilic center?
The OH.
Good. Okay, so the OH is the nucleophile. And then as in the nucleophile, which atom is doing the donating of the electrons?
The oxygen.
Good. So the oxygen is therefore the nucleophilic center. Does this distinction make sense between the nucleophile and the nucleophilic center?
Yes.
Okay. Now, how about the electrophilic center? So take a look at the products and to help identify what the electrophilic center is.
The sulfur.
Okay, so close. So let's look at the starting product, right? So we have sulfur with 3 methyl groups attached to it. And then in the product, we have the sulfur with 2 methyl groups attached to it, with now a methyl group attached to the OH, okay? So remember that when the nucleophile attacks the electrophile, right, there's a new covalent bond formed between the nucleophilic center and the electrophilic center. Okay, so now that we have this new bond between the O and the CH3, or the C of the CH3, which atom on the electrophile is actually the electrophilic center?
Would it be the carbon?
Yeah, good. So this one's tricky because your first instinct is to say that the thing with the positive charge is the electrophilic center. But if we look at the products, we see that the electrophilic center is actually the carbon. So this would come in like this, and then the electrons get bumped onto the sulfur. So with that, what is the leaving group in this particular reaction?
The CH3 with the sulfur.
Good, yeah. So this piece right here is going to be our leaving group, right? And so that shows up here, which shows the leaving group. And now we have this new covalent bond formed between our nucleophilic center and our electrophilic center. Any questions on this? Okay, so why don't you take a couple minutes to try the last practice problem. And so use the curved arrow notation to help you complete this association. Now, remember what I said earlier about maintaining overall charge between the reactants and the products. Okay, so the product might seem kind of strange, but stick to the rules that you know. Okay, so maybe one more minute on this. Okay, so let's take a stab at this. So what do we think? Which molecule is going to be donating electrons?
The oxygen. The oxygen.
Good, good. And what molecule or which atom is going to be donating those electrons to?
The carbon.
Good, which carbon?
I was thinking the way I did it, I was thinking it would be to one of the methyl groups instead of the main central carbon.
Okay, so in this case, it will actually be the central carbon. I know it's kind of confusing. So sulfur and carbon have very similar electronegativities. And so some different things can happen there. In this case, since we're dealing with just the carbons, right? We want to help satisfy that carbon's octet, right? And so if we were to attack a methyl and say, make something leave, right, as a leaving group, then we would have electrons going on to the carbon, and the molecule just won't be as stable, okay? So one thing I should mention is also not in every case is there a leaving group, okay? So this will also come up in future lectures, what makes a good leaving group, and the instances in which you should expect to see one, okay? So we know that the oxygen is going to be donating our electrons to the carbon. And so in this case, we actually do not see a leaving group, okay? So our final product is a new covalent bond formed between our oxygen and that carbon with the plus charge to make this molecule. So again, like I said before, it's might be kind of strange that you would leave this molecule as having that plus charge on the oxygen. That might be kind of weird to see. But you could then react to this molecule with, say, a base to remove the acidic hydrogen and reduce the formal charge. But in this instance, this particular reaction, we want to maintain the overall charge between the reactants and the products. And so our resulting molecule is this one. Are there any questions on any of this stuff?
I have a quick question.
Mhm.
So that arrow you drew from the O going to the C, that's how you would do the curved arrow notation?
Exactly. Yep. So the electron source, right, is going to be, so I picked those two electrons, right, on the oxygen. And so the head of the arrow is going to point at the atom that receives the electrons. And so this will be your curved arrow formalism for this particular reaction. Yeah.
All right, thanks.
No problem. Anything else? Any other questions? Okay, if not, I can turn it back over to Corel. So I will stop sharing. Yeah, thanks guys.
Hi, everyone. How many people are planning on staying? Just so I can get a idea.